we are working in hard homogeneous spaces, which means that if you take a group element and apply it on a set E, it will go to another set E prime. If this G is a cyclic of order n, then we can define it as a bracket notation of AE, which is equal to G to the power of A acting on a curve. This star means group action. And we say the hard homogeneous space is symmetric if it is possible to compute minus AE from AE, minus AE0 from AE0 around E0. There are a few assumptions that we are using in these papers. The first one is a vectorization problem, which is analogous to this problem, which says that if we have AE, it's difficult to find A. And the other one is multi-target gate, which is saying that if we have a multiple of these curves, finding the differences between these curves are still difficult. And the next assumption, which is new, which says that vectorization problem, which is that vectorization problem with auxiliary inputs. It says that if we have AE, and A is the secret, and the coefficients of A, I mean, these CIs are chosen from an exceptional set, and they are public. Even if we have these CIs public, still finding A is difficult. We have a CSI-DH key exchange, which is analogous to the Diffie-Hellman key exchange. It says that we have two parties, Alexander, they want to exchange a key between each other, they want to achieve the same key. So what they do is that Alice applies her secret on a curve and sends it to Bob, and Bob gets this updated curve and applies his secret on it as well. And the same goes for, I mean, both they do the same, and at the end of the day, they get curve EAB, the same curve. And okay, here we do not have any moments. With AE0 and BE0, we cannot do anything because we do not have homomorphism. Okay, in isogeny-based cryptography is divided into main branches. The first branch is SIDH, and the other one is CSIDH. SIDH was broken by Kirikawa attack in 2022, but CSIDH is still alive, and our protocols are in this setting, CSIDH setting. In this setting, we have two non-signature schemes, which the first one was a C-fish, given the family of this but yeah, in 2019, and then in 2023, C-shark came out, which is more efficient than, more shading friendly than C-fish. We will see why. In C-fish, we have K different, the public is K, the public is calculated with K different curves. I mean, the public is EI equal to XI is 0, and these XIs are independent. And in the C-shark, the authors noticed that they observed that the distributed key generation of C-fish is very slower than its signing algorithm. Even sometimes it becomes like 4,500 times slower. And at the same time, there was a paper which proposed this structure public keys. I said the assumption behind that, this vectorization assumption that I said, if you have these CIs, CIs public and which is chosen from exceptional set, still finding this X is difficult. So this gives K different curves, but with just a single second key. And yeah, they applied this search a public key to C fish, and they got C#, which stands for C fish with shading friendly keys. And this is as efficient as C fish, but it has single secret key, which is good for threshold when we want to distribute it. Since when we want to distribute, you need to distribute keys, so when we have just one single secret key, it makes life easier. Okay, let's move to identity-based, identity-based cryptography is the first time defined by Shamir in 80s, and identity-based signature is again the first time defined by him. And like in the standard signature, we have three algorithms: key generation, signing, and verification. I just avoid writing this key generation, it doesn't matter. In the signing algorithm, signer signs a message using her secret key. And in the verification algorithm, verifier verifies the signature using the signer's public key. In IDS, I will call it IDS, in identity-based signature, in IDS, the signing algorithm is the same. Signer signs with her secret key, but the verification algorithm is different because verifier checks the signature with the identity of the signer. A very naive way to have IDS from a standard signature is that somehow we have a certificate for the public key or the ID of the signing. In this way, it means that somehow we have a dealer who signs the ID of the signer, and then and outputs a secret key for her, and then the signer using this secret key signs the message. Basically, it has this is like a certificate, but certificate is itself like a signing something. And the signer signs and calculate this signature of certificate and this certificate. And for verification, a verifier needs to verify these two signatures. Is that good? Not that much, because it needs a lot of space, since we have a certificate beside message, so it needs a lot of space, and we have two verification. This is not that much good, but then people started working on them and make them better, and at the end, Baek and Zheng in 2004, they proposed descriptor-based ideas, and respectively they proposed the threshold version of this signature, which I will not go through all the details, but just I will say very high level to give some idea that how it works. Instead of like they take hash of ID of signer, the hash of the ID that they want to, the hash of ID of signer, and set it to public key of user. And then the dealer takes sets the secret key of user equal to G to the power of the secret key of the author itself. And then basically somehow in extract, I forgot to say that. In IDS, we have 4 algorithms: extract, setup, extract, signing, and verification. In setup, which we are setupping something, and we get the public parameters. In extract, somehow dealer signs the ID of signing signer, and then in the signing, signer signs the message using this secret key, and we have verification, which verifies using the ID. Verifies somehow with the public key, but the public key is, I told you the public key is said to be hash of ID. Then want to sign something, they are signing with Sigfish signature. In the setup, they set EI equal to SIE0. These SIs are the secret key of authority. And in the extract, yeah, exactly the same. They are kind of signing. You can see here, I mentioned, yeah, this is the signature, how the signature of Sigfish works. Like first she commits to one random RI using this group action, and then this is a challenge by getting hash of ID concatenated with RI. We have a challenge, and then she opens using this operation. And yeah, and then the rest of kind of the same. The signer signs the message using this secret key that here you can see. The verification is also the same. Checks with ID. And yeah, the normal question for me, at least, is that can we have a post-quantum t-shirt version of these signatures from Isogenies? And the answer was yes, but I tried to do it with the shading-friendly version of Sigfish, which is C#. So the first contribution of the paper is that this is a blueprint of Shahla Atapoor's paper, I needed to adopt this word with C#. And here you can see, instead of having K difference secret and K difference SIs, I am using the idea behind the C#, I mean CISIs, when CIs are public and chosen from exceptional set. This is a structure property. And then I set this, so here you can see that we have a smaller, in the paper I call this SK, the secret key of authority, the secret key of authority, I call it master secret key in the paper. And then here you can see that instead of having K difference SIs or secret keys, the master secret key becomes shorter using just C# idea. And yeah. Then I have two more contributions, which the first one is identity-based tissue signatures, which is secured with a board, and the other one is the robust version of that, which guarantees output delivery. But before that, let's go through the standard tissue signatures in Isogenies, how they work. I said that in signatures, the standard signatures have key generation algorithm, signing, and verification algorithm. But then when we want to distribute it, we just distribute key generation and signing algorithm. And because of that, I avoid writing verification here. In here, the threshold signatures and the standard threshold signatures have two main parts. The first one is distributed two main algorithms. The first one is distributed keygen, and the other one is distributed signing. Distributed keygen itself, again, has two main parts of verifiable secret sharing, and the other one is public key computation. In verifiable secret sharing, basically we have a secret, and we share, this secret is shared among the parties, and in public key computation, parties use their shares and compute the public key using the round robin. What is round robin? Imagine that our public key should be this EI equal to AE0, and this A is shared among two parties, Alice and Bob. Alice has A R and Bob has A B. And here, Alice with having, ER E0 and B has ABE0, what they can do with that? Nothing, because we do not have homomorphism. So what we do is, in the first slide, if you remember, I said we have CSIDH key exchange. Something similar happening here. Alice round robin means that Alice applies her secret on curve E0 and gets a new curve and sends it to Bob, and Bob then updates the new curve with his secret. And it goes to the last party and then public is out. And then we have distributed signing. I mean, it means that a set of parties come together and can sign. Okay, and now in identity-based digital signatures, what we have in this area. I mean, this consists of 5 algorithms and not 4. Just this algorithm of the keys are extra than the IDS. Okay, this is the structure that this is the algorithm, this is the protocol that I have for my first IDTH with a board, and I will explain one by one. The setup is kind of the same as IDS, it's the same. The extract is run. This is not like the normal digital signatures, which I said even the key generations are distributed. Because here extract and that algorithm, the keys are run by dealer. And here the dealer signs the ID, and their dealer shares the secret, which is the output of extract, shares among the parties, and then parties in the distributed signing algorithm parties can come together and first get these public keys, complete the public keys, and then they can sign it. Yeah, in this decayed algorithm, I mentioned that the dealer just shares the output of this extra algorithm. And here you can see that. Here you can see that for signing algorithm. In the next slide, you will see why I just want to say think about it, because here for signing algorithm, somewhere at some point, parties are opening some subtraction of some values. They open Fi minus Ri, and they get Zi. And at the end of the day, we somehow sum up these Zi's. So if someone is cheating somewhere, then we will realize when the protocol runs completely, and then when we sum up these Zi's, then we can realize that, oh, someone was cheating somewhere, okay, then we are going to abort. Because of that, this is secure. This is one thing that I wanted to mention here. And the other thing is that, what if the signers do not use the secret that dealer gave them? What if they change? This was a flaw that was in Sashimi and C#, they realized that they can cheat, and they said that the Sashimi is a threshold protocol signature, and it is a full threshold, because all the parties, if all the parties are there, then by summing up this, they can find that something went wrong somewhere. Yeah, this is the first algorithm. The second one is robust. Okay, the cost of having this robustness is having a longer public key, because somehow everything is similar. Just here, I am using the idea of treasure shard in this paper given to 2023, and the thing is that dealer here in this algorithm not only shares the secret among the parties and sends privately to each party her or his share, also the dealer commits to their share. So then here they cannot cheat and use other secret key, they have to use their shares. And yeah, because of that I said that we have, this helps us to realize who is cheating, and okay, here I can tell that. Here also, the idea is that instead of opening the subtraction of two values. Here we just open fx minus rx, and we get a polynomial. This way, and by having these commits from here, that we call it in the paper verification keys, which dealer gave out and broadcasted, then we can find the malicious party, we can find which one, who is cheating, and then we can reconstruct his or her share, and we can continue. And we can say that, okay, we have brought it out with delivery. What I wanted to say here is that, okay, I said that one, and I said this one. Yeah, I think, yeah, whatever I wanted to say, yeah, we have. Then I conclude my presentation with this, that in this paper, we have two identity-based digital signatures, one with a shorter public key but secure with the board, and the other one is a robust identity-based digital signature but with the cost of longer public key. At this point, they are not practical. This result is theoretical because, you know, we are doing a lot of group actions, and each group action somehow takes, I think about 35 milliseconds. So it's too much. I mean, it's not practical, but it's good actually. But then, as a future researcher, I can say that we have, I have here two research directions. The first one is, can we do efficient group action? Can we have a more efficient group action? Which a lot of people are working in the Isogenies areas, and they are working on this to make it group actions faster. The other one is, can we have adaptive version of this IDS from Isogenies, and respectively this identity-based digital signatures, because we have adaptive version of the, this will go base. So can we have the adaptive version of these things that I have in this paper? I don't know, maybe. Thank you very much for listening.